Hello and welcome back. This is Jonathan Gardner. We're covering, I think this should be considered the second tutorial in the Python language. This is intended for beginners, for people who have never programmed before. There are two previous videos you should have watched up to this point. One is the Python interactive mode video to learn how to get into Python interactive mode. You'll be using Python interactive mode to do practice and to try things out to see what happens. You should have also watched the last video on decimal literals and integer math. So let's begin. First, we're going to have to cover something called base n. This is a math topic that rises typically in algebra. But if you notice that when you have a decimal number, like let's say 1735, right? So this 5 here is only worth 5. This 3 here is worth 3/10, 30. This is 700. And this is 1000. And this seems pretty natural, but this was a revolutionary breakthrough in the history of numbers to write numbers out this way. The Romans didn't figure it out. So we add all those up and we get the number 1735. And we notice that this is decimal. Decimal is base 10. And there are 10 numbers, 0 through 9, that you can use. Okay. It doesn't go up to 10, it goes up to 9. So it goes up to 1 less than the base number. Okay. And each position is worth 10 to the position number. Okay. In this case, the position is 1, 2, 3, and 4. So 10 to the 0, that's equal to 1. 10 to the 1 is equal to 10. 10 to the 2 is equal to 100. And 10 to the 3 is equal to 1000. Okay? That's how decimal works. Let's talk about binary. Binary is base 2. And you might be wondering how you can get along with this, but it actually works quite well. And there are 2 digits, 0 and 1 are the digits. We call them bits. Binary digits, bits. And each place is worth 2 to the place number, the position. So the first position in binary would be worth 1. The second one would be worth 2. And then 4, 8, 16, and so on. Okay, and so a number like 0, 1, 1, 0, well, this is going to be worth 0, this one's going to be worth 2, this one's going to be worth 4, and this one's going to be worth 8. So the total, 0, so the total is 6. So in decimal, this number 0, 1, 1, 0 in base 2, and I'll put a little 2 subscript here to remind you that it is in base 2, is equal to 6 in base 10. Okay, now in decimal, we can add fractional components, so we can select 2, 7, 5. This one is the tenths place, so that's 2 tenths right there. That's 7 100ths. And this is 5 thousandths. Okay? And you can do the same in binary as well. So if we did 0, 1, 0, 1.1101, then we would have, this would be, let's see, the half, quarter, eighth, 16th. This is 1/16. This is 1 quarter, 1/8, and this is worth 1, and that's worth 4. So this is 5 point, let's see what that would be. Some number, 1/8 plus 1 quarter plus 1/16. So if we convert this all to 16ths, this would be 4/16, and this would be 8/16. No, 1/2, I'm sorry, 4/16, 8/16. So we'd have 5 and 9, no, 8, 12, 13, 13/16. Okay? That's how you would do that. So you can have fractionals in this as well. This will be important when we do floating point numbers. So right now I'm just going to mention it and don't worry about it too much. Okay? All right. So in Python, a binary literal starts with either 0b lowercase or 0b uppercase. And typically we use the lowercase 0b. And then you can have digits 1, 0, 0 or 1, 1 or 0. And you can use underscores as well to separate out the bits if you wanted to, something like that. All right. And same thing down here. You can have 0, 1, 1, 0, 1, 1, 0, 1, or whatever you want. Okay? And that's how you do binary literals in Python. Let's do octal. So octal is base 8. Okay? Means you have digits 0 through 7. And the places are worth 1, 8, 64. After 64 comes 512, 4096, and then 32768. Okay. Octal typically isn't used. It's more of a relic from the past. The ASCII tables typically were listed in octal, so people had them memorized in octal. For instance, in octal, 101 is equal to the letter A. We'll talk a lot more about ASCII and Unicode in a later lecture. In Python, if you want an octal number, you preface it with 0O or 0 capital O, and for obvious reasons, we prefer the lowercase 1. And so in this case, 101, that would be the number that would represent A, which is, I believe, 65 in decimal. Okay, and the last one to mention is hexadecimal. Hexadecimal is nicknamed hex, so you'll often hear people say hex instead of hexadecimal. This is base 16, and it has digits 0 through 9, and then we need additional digits for 10, 11, 12, 13, 14, 15, so we're going to use the letters A through F. Okay, so A is worth 10, and F is worth 15. Okay, and the places in hexadecimal are worth 1, 16, 256, and then 4096. Then we have 655, 536. So it grows rather rapidly in its thing. And in Python, we will do hexadecimal by putting a 0x or a 0 capital X. We prefer the lowercase, and you can use uppercase or lowercase letters. So for instance, this is a valid hexadecimal number. Okay, it looks like dead beef, but it's not. It's a particular number. I don't know exactly what number that stands for, but it is a number. Okay, and of course you can have underscores in there as well. You can have underscores in the octal, so 101 if you really wanted to. Notice that hexadecimal, because it's base 8, so one octal digit represents 3 bits, and base 16, one hex digit, gives you 4 bits. Okay, and we can write those out right here. Okay, so we're going to have 0, which is represented in binary. I'll do binary 0B 0000. Okay, and then 1 is 0B0001, 2 is 0B0010, 3 is 0B0011, 4 0B0100, 5 is 0B0101. I think you see the pattern developing. 6 is 0B0110. 7 is 0B0111. And all 3 bits are filled here. And so we have to move past the octal. And so we're going to go up to decimal and then hexadecimal. So next is we have 8. That's going to be 0B1000. 9 is 0B1001. 10, oh, this is A actually. A is 0B1010. B is 0B1011. C is 0B1100. D is 0B1101. E is 0B1110. And then finally F is 0B1111. And that's how the hexadecimal digits and the octal digits relate to binary. All right. I'm going to talk a little bit about how you can sound smart as a programmer. And this really does make a difference. It's somewhat annoying to have conversations with people that don't know the powers of 2. Okay, so let's memorize the powers of 2. I'm going to show you some tricks. Okay, first we have 1, 2, 4, 8, 16, 32, 64, 128, and then 256. Let me write that out better there. This is 2 to the 8th. Okay, this is 2 to the 7th. Right, that's the last. So basically, at this point, 2 to the 8th, this is 2 hex digits. Okay, and then we have 2 to the 6th here, 6 and 64. It's pretty easy to memorize. 2 to the 5th. I don't know a way to memorize this, but just 5 and 32 are related. 2 to the 4th. So 2 to the 4th is just 2 to the 2 times 2 to the 2, so it's 4 times 4. 2 to the 3rd is 8. 3 kind of looks like 8. Then we have 2 squared. And then we have 2 to the 1st power is obviously 2, and then 2 to the 0 power is 1. Okay? These ones you absolutely have to memorize. It's very frustrating to talk to people that don't know that 64 is 2 to the 6. The next ones you have to memorize is 2 to the 10. Okay? That's going to give you 1024. And if you notice, this is very close to 1000. So we have called this K in the past. Okay? Now there is, in SI, standard notation, right? You're going to have kilo means exactly 1000. But here we're saying K is equal to 1024. Okay, because it's so close. Technically we should be using KI, which stands for kibi, which is the binary prefix, but this really hasn't caught on yet. We still use K. When we're measuring memory, we're talking in units of 1024 for K. When we're talking hard drives, they're going to use the kilo, the 1000. Okay, so the hard drives are slightly larger than they are. Okay, 2 to the 20, that is going to equal 1K times 1K. We use a star here because that's what we do in Python. And this is going to be called 1M, which is a million. Okay, and mega is what we typically call it, but mebi is the more technically correct name. 2 to the 30, this is 1K times 1M, which is going to give us 1G, which is a giga or giga, okay? Or gibby or jibby, I think, is what you're supposed to do if you use the binary prefix notation. Okay, 2 to the 40, this is 1K times 1G, which is 1 tera, tera. So terabyte is 1,000 billion bytes, okay? And then 2 to the 50, this is going to be 1K times 1T, and this is going to be peta, so 1 petabyte, okay? And unless you're dealing in a large corporation or your business is all about managing large amounts of data, you probably will never talk about petabytes. All right, 2 to the 60 is 1K times 1P, which is 1E, which stands for exa, okay? They say XB in the binary prefix. And this, we're starting to talk about numbers that start to compare with all the data stored. I think back in 1995, they were at the exabyte range for all the data you can possibly store. Nowadays, we can go beyond that. However, note that if you have a 32-bit machine, that means the computer, the CPU, deals with numbers up to 2 to the 32, right? So that would be in the gigabyte range. So this is going to be 2 to the 32. 2 to the 2 is 4, so that's 4 gigabytes, okay? Or gigabits, right? 64 bits is 2 to the 64. Well, 2 to the 4th is 8, so this, or 2 to the 4th is 16, so this is 16 exabits, okay? So this number is truly huge and truly large. I don't think we'll ever see 128-bit computers because there's really no need for that. Maybe somebody somewhere will discover an algorithm that needs that kind of precision, but I don't know about it. We'll continue in the next video with how Python organizes the data in memory. Take care, guys. Bye-bye. This video is part of a series on the theory of Python. You can click on the left to see the playlist and on the right to support my channel. Thank you very much for your time.